we will show what kind of statement that we will be dealing with in this course. So we define many concepts and we will define more, and then we will see the relationship between these concepts. And one of them is this theorem by Koenig. So we define this concept of being bipartite. And we define this concept of cycles. And these cycles are actually quite useful in terms of dealing with lots of concepts in graph. And one of them is that you can characterize this bipartite graph using cycle. So a graph is bipartite if and only if it has no odd cycles. So we can prove this. So you might think that this is more of global condition, that every vertex is partitioned into two so that each of them are independent set. And this is more like whether it has this certain local substructure or not. But these two has this seemingly not obvious connection. And then how do we prove this? We can prove this using this lemma. And what's this lemma? So here, what's odd cycle means? Odd cycle means cycle with the length being odd. And similarly, you can also consider odd walk, odd trail. And this lemma says that if you have a odd closed walk, then there exists, it contains the edges of an odd cycle. We can prove this. Again, the proof uses the minimality. Let's say we are given an odd closed walk W, and we take the W prime, which is the minimal odd closed walk contained in W. And to be more rigorous, we consider this W in a cyclic way without starting vertex. Yeah. Then what happens if you have a closed walk which is not a path, then not a cycle, then it might look this way. And if this is not cycle, then a vertex repeat. And if this happens, a vertex repeats in this W prime, then what do we know? This splits the work into, say, this part and this part. And once it's splitted, the length of this part plus length of this part is the length of the entire one. And the length of entire one is odd. That means it's split into an even closed work and odd closed work. A contradiction. So this odd closed work is smaller one to the minimality. So this proves that if you take minimal old crosswalk contained in W, that must be an old cycle. So this lemma holds. So now let's prove the Koenig theorem. So one direction is clear. So this direction. If you have a bipartite graph, and then all the edges are between, then you start from one part, and you move, then you are in other part, and then you move, you are in other part. So if you take a walk, it is walk in a bipartite graph must alternate between the parts. So every crosswalk, if you want to come back to the starting point, then you have to cross even number of times. Hence, also every cycle has even length. So this direction is clear. And the other direction is where is less trivial one. So what happens if G has no odd cycle? What do we have to do? Assuming this, now you want to find the bipartition of a graph. And finding bipartition is same as color all the vertices with one color and the other color, so that there are no edges between the same color vertex. So you actually do that. You actually assign the colors in each vertex. So consider a component C of G, so connected component, and we choose a vertex U in C in arbitrary way. And for each vertex B in C, we take a walk between them. So if there exists an even UV walk, then we label B as the even vertex. If there exists an odd UV walk, then we label B odd. Then what do we know? As this C is a connected component, if C is connected, all vertices in C gets a label. And moreover, this label is well defined, because if a vertex B gets both label, then what? You have a odd work from U to B, and then you have a even work from U to B. Then you can combine those two work. That yields an odd crosswalk, which is a contradiction. Because why? If you have an odd crosswalk, then this lemma says that there exists an odd cycle, but we assume that there are no odd cycle, so which is a contradiction. So this defines the label of all the vertices, and you can partition the vertices into even vertices and odd vertices. And so we need to check one more thing, so that this is actually bipartite graph, meaning that the vertices with the same label are not adjacent. if you have a h, x, y in this component, and then what do you get? You take a ux walk, you take a walk from u to x, and then we take the edges. Then it yields a u, y walk of different parity. Hence, this shows that every vertex gets uniquely labeled, and then every adjacent one gets different label. So this labeling is a bipartition of GC, G induced by C. By taking disjoint union, over all components, G is bipartite. So this proves the theorem. So this establishes connection between two, different concepts. And let's prove one more proposition of the similar type. When I say similar type, means that it relates to different concepts. So when we have a graph G with the minimum degree as delta, which is at least 2, then it contains a path of length delta and a cycle of length at least delta plus 1. So this again provides some connection between two different concepts, the minimum degree and paths of certain length or cycles of certain length. So let's prove this. So what do we do? Again, we use the minimality or maximality. So in this case, this is maximality. So let V1 to Vk be a longest path. In G. So there could be multiple longest paths. You take one of them. Then what do we know? Then what we know is that if there is other vertex here, which is adjacent to Vk, and this provides a longer path. So that doesn't happen. Again, if there is some vertex adjacent to this, then this provides a longer path. That's not happening because it contradicts the maximality of this longest path. Then what? All the neighbors of Vk lie in P1 to Pk minus 1. Otherwise, we obtain a longer path. So we have that k minus 1 is at least delta, and k is at least delta plus 1. Hence, this path has length at least delta. And this is the giving the path. And then how do we find the cycle? What is cycle? You have a path, and then somehow if you close it, then it is a cycle, right? So what we do is we again use the maximality or minimality in this case. So let I be the minimum I such that Pi Pk is an H in G. Then what do we know? Because we assume that delta is at least 2. This Pk has a neighbor other than this Pk minus 1. And then that, because of the maximality of this path, that's not, this H is not going out, this H is going in. Then the neighbors of Pk lies in Bi to Pk minus 1. Because of this minimality, it doesn't send, Pk does not send any H's to the previous parts. So we have K minus I is at least delta. Hence, Bi to Pk and then coming back to I, this is a cycle. Cycle of length at least K minus I plus 1, which is at least delta plus 1. So this proves the proposition. And this proposition is best possible. Meaning that if you have a minimum degree delta, then try obtaining longer path and longer cycle is not necessarily possible. So it could be impossible for some graph. So that question is that not the question, because what? We consider a complete graph. A sub delta plus 1. Then minimum degree is what? Delta, but no path of length delta plus 1 and no cycle of length delta plus 2 or longer. So this proposition is best possible. So we show these two statements. And if you kind of see, then this is more of a qualitative statement. There is some structural information about the graph, and there is also structural information about the graph, and then we provide some connection. On the other hand, this one is more quantitative statement. This length of a path is something that you measure. It gives you some number. And then this minimum degree is also a number. And then you compare some inequality between them. So one parameter being this big, then the other parameter also has to be this big. The relationship between this quantitative statement. And it is not a clean cut of the graph theory to two, but in many cases, structural graph theory deals with more of this kind of a question or theorem. And extremal graph theory is more of dealing with this kind of question. Maybe the name structural graph theory is obvious why it's called structural graph theory. But extremal graph theory, why do we call it extremal graph theory? Because here, you take a example which is almost satisfying the relation, but not. So this is called extremal example. So you have this parameter, and then you want to say take this parameter and this parameter. You want to show that the inequality between them, but how close can you make the inequality? You can make it tight. Then you want to find tight inequality. Then this is extremal case. If this inequality is tight, and then this is no longer tight. If you add one, then this is no longer true. So this without one is the extremal case. So it studies about the extreme situation, the relations between these like a parameter. So it's called extremal graph theory. So yeah, in the next video, we will get back to the definition of connection. So we define these paths and connected graph. And then we will study about the connected graph in the next video.